Okay, so once again, you had this table. The table's over here. The table really has 4 numbers, 100, 20, 50, and 30. And then somebody very nicely added the numbers, right? 100 plus 20 is 120, 50 plus 30 is 80. And then they added them this way too. 20 plus 30 is 50, and 100 plus 50 is 150. If you know how to read the table, this should take like 1 second. So let's see what you guys said. What's the probability of A? All right. Reveal what people said. Will it do it? Okay. 69 people said 150 out of 20. 150 out of 20. Let me move the timer. So A, 150 out of 20. There's 150 total people who are A's, right? 100 of them are B and A, and 50 of them are A and not B. And then how many people total are there? 200. So what's the right answer? 150 out of 200. I think. Reveal correct answer. Makes sense to me. Very good. Most people got that one. What about the next one? Let's go back to... What about A given B? What about A given B? 60 people said 100 out of 120. 100 out of 120. So when you're given B, that means for you, the whole universe is only people who have B. It's like you took everybody else and you like Thanos snapped them away. They're gone, okay? These people, all these 80 people, they are removed from the universe. So there were 200 people originally. You remove 80 people from the universe. How many people are left? There's only these 120 people. And out of these 120 people, 100 are A. So what's the probability of A given B? In this problem, it is exactly what 60 people said. 150. 100 out of 120. There we go. All right. Just over 2/3 of people got that right. Any questions or comments about how to read the table or what's going on in the table? From the 1/3 of people? Maybe the 1/3 of people all understand now. Maybe it's still unclear. Please ask. Yeah. Okay, so there's 120 people who are B's, right? We deleted, you should delete everybody below this point gets deleted from existence, okay? That's what given B means. Given me B means take everybody who's not B and remove them from the universe, okay? So these 80 people are all gone. We had 200 people total. We deleted 80 people. We are left with 120 people. Out of those 120 people, some of them are A's, some of them are not A's, right? Everybody is a B because we deleted everybody who wasn't a B, right? Everybody who's left is definitely a B. That's what given B means. The probability of A given B, right? So 120 people total. How many are A's? What is the probability of A in this new universe we're working in where we're given that B is definitely true? 100 out of 120. The probability of not A is 20 out of 120. But that's the right answer. Did that help the second time? Anybody else? Please let us know. This is why we do the course. Yeah? The first one. Yes, let's do the first one. So in the first one, this is before we've done anything weird to the universe. So there's 200 people total, right? And we're asking, out of the 200 people, how many are A? And the answer is there's 150 people who are A. The 150 people, they come in 2 flavors. There's people who are A and B, and there's people who are A and no B. But the 2 flavors together, 150 total people who are on team A. And so what's the probability? 150 out of 200. All right. Last but not least, are A and B independent? Let's cover up the answer like you might not see it. Are A and B independent? Okay. 49 people said no, not independent. 35 people said yes, independent, and 5 people said not enough information. The correct answer is they are not independent. No, not independent. Okay. Seems like that was the hardest part. You guys calculated this, and you calculated that, but this was tricky. What to say? Whether or not it's independent is some very specific thing you do to these 2 numbers. So you take these 2 numbers and you do something to them. And then based on what you do to these 2 numbers, the answer is either yes or no. I will let you guys discuss for 1 minute. What do you do to these 2 numbers? This is a review from last class. discuss amongst yourselves for 1 minute, and then I'll take an answer. But what you have to do to these two numbers to decide if they're independent or not. You go think about it.
Discuss the answer on that as I continue with the slides, because the next thing I'm filling in all of those probabilities.
I see. Okay. Well, okay, so you want to not take it up? Gary will tell you?
Yes.
Okay.
Yes.
Okay, great. So hopefully time is up. Let's come back together as a class. All right, thank you very much. So hopefully you discussed, and the people near you helped you figure out what is it the thing you have to do to those two numbers. And instead of telling you the answer, Gary's going to tell you the answer. We're going to see some more slides, and then we're going to see the answer as we go.
We're going to continue the discussion of this problem here. And let's see. I'm going to leave this one behind now. And I'm going to freeze that one. I'm going to switch back to HDMI laptop. We've got that. And so we left you the job of working out all of these probabilities and asking the question, are A and B independent or dependent? And if we work through all those probabilities, I'm hoping you did attack them, you should have found all of these answers. And the mathematize, and this thing is being incredibly obnoxious. Why? Because it's following me around on the floor. Let's just see if I can get it to be quiet. I'll attach it to my tie. That seems to work. Okay, so among the ones we just had with mathematize, probability of A was 150 out of 200, was 0.75. Mihai's already gone through the explanation of that. The probability of A given B was 100 out of 120 equals 0.833. Some other interesting things on that. One is the probability of A intersection B is 100 divided by 200. Where was A intersection B? This was the 100 here out of the 200 people in all, 100 and 200. That was probability of A given B, and also notice there's also a probability of B given A. So you kind of keeping those things in the right order is important, and the key thing is to start off with the idea that the thing past the condition sign, the thing past that is the condition, and that tells you where to restrict your sample space, where you reduce your universe to. So if I say the probability of B given A, the probability of B given A says I'm given A, I'm given somebody who has trait A. I am ignoring those who don't have trait A. And of those who have trait A, 100 of them have trait B. So it's 100 out of 150. So again, notice the difference between the probability of A given B and the probability of B given A. Very, very important because people do mix it up all the time. And once you got it straight, you can be pretty clear on it. So then we threw in a couple with complements on it. So, for example, the probability of A given not B, probability of A given not B. Okay, well, we're looking at the universe consisting only of those who don't have B, don't have trait B. We're ignoring those who do have trait B. So of those who don't have trait B, how many have trait A? It's 50 of them, 50 out of 80. 50 out of 80, 0.625. Similarly, I can ask for the probability of B given not A, in other words, A complement, and of those who don't have trait A, of those that don't have trait A, there's only 50 of them. But of those, 20 of them have trait B, 20 out of 50. And we could ask things like the probability of A complement given B complement, and the probability of A complement given B, and so on and so forth. This one here is probably the trickiest one, the probability of A union B. And what we have to say is which are the individuals that have trait A or trait B, or both is included. And so we have, these have trait A and trait B, these have trait A but not trait B, and these have trait B but not trait A. But the point is there's 170 of them. In fact, the only people who are not included in A union B are those 30 people right here which have neither trait A nor trait B. So the question is, are A and B independent? There's several tests you could use. A simple test here, given that you were asked for the probability of A and the probability of A given B, is, are they equal? If they're equal, they're independent. And what happens is, if they're equal, it simply means knowing information that B occurs gives us no information for revising the probability of A. But here we do change our probability for A if we know B's occurred, as opposed to if we know nothing about B. Similarly, if we looked at the probability of A given B complement, again, that probability gets revised. If you compare the probability of A, if I know nothing about B, it goes, we raise that probability of A if we know that B's occurs, and we decrease that probability if we know that B didn't occur. And you could look at it from, similarly, is the probability of B equal to the probability of B given A? It is not. Similarly, it's not equal to the probability of B given A complement. Again, you revise your probability based on your information. Whereas when we did case 1, and I'll just come back to case 1 for a moment. In this one, the probabilities were set up, the table was set up so that the probability of A given B was equal to the probability of A. And so the probability of A given B is equal to the probability of A. The probability of A given not B is also equal to the probability of A. They were independent because knowing whether B occurred or didn't occur gave us no information for changing the probability of A. It gives us no extra information that allows us to revise the probability that A will occur. Okay, so we did those 2 cases, and what I want to do is quickly sketch out. That's weird.
You were just over.
Oh, there it is. Sketch a Venn diagram for each of the two cases. Okay, so I'm going to come back and start sketch a Venn diagram for case 1 initially. This is a nice one, and we worked out lots of numbers, and that was the table. We've got the table, and we worked out various probabilities. Okay, so I don't need all of these things, but maybe I'll start with work with those numbers there, case 1 situation. So learning how to sketch Venn diagrams quickly and efficiently. Overlapping circles. Okay, and hope this isn't too blown up. So here's the basics on drawing Venn diagrams. First of all, always draw a rectangle. When I see a Venn diagram without a rectangle around it, I'm appalled because you haven't delineated your sample space. Okay, and that sample space, label it X. And then you draw your events in there, and the good way to start is simply for your events A and B, draw overlapping circles. We can revise these. We'll see that there's going to be cases that we revise our diagrams based on probabilities, but if you start with 2 overlapping circles, it works nice. Okay? Label them outside the circles. And the reason for labeling them outside the circles rather than inside the circles is when you label them inside the circles, we'll see that you can get confused as to what area is what. Because what you notice is that within A, you end up with 2 areas. And within B, you end up in 2 areas. And where they overlap, that's the intersection of A and B. But you notice that there's sections of A that, a section of A that doesn't, that isn't in A intersection B. Well, what is that? Well, that's the area of A that's outside of B. That's A intersect B complement. Okay, where A occurs and B does not. And similarly then, this is A complement intersection B. Okay, A doesn't occur, but B does. And why do I want my rectangle on there? To emphasize that there's another area outside those circles, which is A complement intersect B complement. Neither occurs. Now, that's labeling the events, and we can kind of think of the probabilities as, we can put the probabilities in there as representing sort of spaces where the total probability for the sample space is 1, the total probability is 1, and then there's areas for each of these things which correspond to the probabilities for that. Are they necessarily proportional? Well, getting them space proportional can be very tricky, so we don't really worry too much about that. But we can go through and we start labeling probabilities, or we could put numbers in. We could have put numbers and said we have 200 individuals in there and put the individual numbers for each of those intersections in. But if we want to make it a Venn diagram for the representing probabilities, we just go through and put the probabilities in. And so let's see what we've got. The probability of A intersection B is 0.45. And what else do we have? Well, the probability of A was given to us originally as 0.75. I'm going to put the 0.75 up there in brackets just to indicate that the whole thing is 0.75. And the probability of B was 0.60, again in brackets because I just want to say that that whole circle has an area of 0.60. And so look at how quickly now I can fill in everything by subtraction. I know that this total area here is 0.75, 0.45 of it's in here, so 0.30 is in there. We've also given you equations. Every probability equation is readily derived from the diagram if you know what to look for. Okay, so Yeah, the probability of A equals the probability of A intersection B plus the probability of A intersect B complement. In other words, A either occurs with B or without B. B either occurs with A or without A. Well, the total area of B is 0.6. Total probability for B is 0.6. The area of the intersection is 0.45. And so that leaves 0.15 in there. And now if we want to get the area for A complement intersect B complement, we can go through and go like this. 0.3 plus 0.45 plus 0.15 is 0.3 plus 0.75 plus 0.15 is 0.9. So that leaves us 0.10 outside, because the total, the sum of the four intersections has to be equal to 1. Now, you may have said, why didn't you, how could you just add those up like that? Maybe you said to yourself, the probability of A union B equals the probability of, just going across here, I'm just going to write it out like this, the probability of A intersect B complement plus the probability of A intersect B plus the probability of A complement intersect B. Or what if you could have just done the probability of A? If you took the probability of A and you added the probability of B, if I took the probability of A, 0.75, and I added the probability of B, 0.6, what would I have done? What would I have done?
Double counted the intersection?
I would have double counted the intersection, absolutely. If I take the probability of A, add the probability of B, I've counted that 0.45 twice, so I subtract it once. Okay? And there's a cute little way you can kind of prove that that goes to that. Okay? Because that plus that gives you the probability of A, and well, then you've got this extra thing, but then if I add the probability of A intersect B and subtract the probability of A intersect B again, I can go to that line. I'm going to leave that for there. So anyhow, we got that particular equation for the union. And now let me just mention something about the conditional probability. Well, I'd like to say more about the conditional probability. People will often say, where is the probability of A given B on the Venn diagram? It's not something that's labeled directly on the diagram, it is a relationship. So if I want the probability of A given B, if I look at, for example, the probability of A given B, I say, well, in given B, that means that I'm restricted to this single circle here. And then what I'm really saying is what proportion of the area within B is covered by A. So I say, well, that's the ratio of this intersection to the area of B. That's where I get the probability of A intersect B over the probability of B. And I can go through and derive similar type probabilities there, like other equations, like the probability of B given A, etc. So that was a Venn diagram. The case 2 Venn diagram, we can...
Gary, you're still frozen on case 1.
I'm still frozen on case 1. Let me think. Because I'm frozen. There was our case 2. And we went through and we did our probabilities. But what's the diagram look like? Well, let's see how quickly we can sketch this one out. Get the little sucker down there. A, B. There's A intersection B. A intersection B was 0.50. What was the probability of A? It was 0.75. So I'm going to put the 0.75 in brackets. The probability of B was 0.60. Okay, and now I can fill in everything else real quickly. Again, the A intersect B complement. Again, remember that's A intersect B. This is A intersect B complement. 0.75 minus 0.5 is 0.25. And what about A complement intersect B? 0.6 minus 0.5, 0.10, 0.6. Oh, out here, A complement intersect B complement, area is 0.15. We've filled in everything there. We can work out conditional probabilities super fast and efficiently. And again, you see we can prove that, for example, the probability of A times the probability of B gives us the probability of the intersection if and only if A and B are independent. 0.75 times 0.6 is 0.45. It's not 0.5. They're not independent. Not independent. Well, okay.
But how did you do it so quickly in your head?
Pardon?
How did you multiply so quickly in your head?
Well, I don't know. Maybe I memorized it.
Okay.
Now, okay. So we did that for case 1 and case 2. I'm going to leave you a couple to work out on your own. Yeah. What am I going to do? Let me see. Relentless. Okay. So, all I did was same probabilities for A and the same probability for B. Probability of A is 0.75, probability for B is 0.6. What I want you to do is get me the corresponding 2x2 table and sketch a Venn diagram for each case. Okay? I will tell you this, that one is pretty standard and one is a little weird. Okay? Guarantee you, one's a little weird. And what are you going to do with that weird case? Okay? But you got to explore it. So I'm going to take that up next week on Monday. And I'm also going to go back and take up those questions I left you the other day, which was, what were those questions? Just a sec, which was it? Those ones, no, these ones. Okay, so I left you these last day, and I'm going to take those up on Monday is my plan. Okay, and if you're going to get the maximum value out of the stuff, what you got to do is try it on your own. Don't just wait till I work through everything. Try it yourself. You get to consult with your colleagues. Make sure you know each other well. Like, you come to a university like Guelph because we have like outstanding students. And you got to get into the socialization of learning. How many people know the people beside you? Do you know the people beside you? Greet the people beside you. Say hello to the people beside you. Okay, and another key thing. Here's something that drives me nuts. I get students who say, I missed class, I have no idea what I'm going to do, where I'm going to get notes. You kind of like make sure you have people who cover for you if you miss class, etc. And you'll do favors for them, they'll do favors for you, etc. Got to get into some like social aspects of education. Okay. That is all I'm going to say for now. I'm going to let Mihai take over from here.
Okay. Very nice. All right, so you might want to write these ones down. I guess these are posted online as well.
These are posted online, and they're slightly revised slides are coming up after this class.
So Gary will give you these, give you the answers soon, but you should try them first. And the other one you should try is to draw the Venn diagram for these two. That's a nice little homework for you guys, and Gary will take that up on Monday as well. Okay, what am I going to talk about for the last 15 minutes? I'm going to give you guys some problems that we can now solve because we know all the tools that we've learned over the past week. And in particular, we are very close to solving the birthday problem, which is what we started the class with. So we're going to see how to do the solution. And actually, you already know everything you need to know to solve the birthday problem. But I'm going to make it easy for you guys we're going to ramp up to the birthday problem in 2 steps. So we're going to do 3. I got 3 problems here. There's this problem, the next problem, and then the problem after that is the birthday problem. You can't see any of this because I'm on the wrong thing. Let's try. Okay. So we're here in Mathematize. There's 3 problems. There's one called 2 cards, same suit. There's one called 3 cards, different suits. And there's one called birthday problem. And really what I'm trying to show you is that you can take what we learned and use it as like a tool. Actually, tools are less exciting. Let's say you use it as a weapon to defeat the enemy, which is the birthday problem, okay? So that's what we're going to do. But we're going to start with this one. 2 cards, same suit. 2 cards, same suit. Let me not let you put any answers in because I want to talk about it for a second. So it's a very simple looking problem. We have a deck of cards, 52 cards in a deck of cards. You remember what a deck of cards looks like. It's got 4 suits of 13 cards each. Who is familiar with decks of cards? Okay, almost everyone. Fantastic. Very simple problem. The deck is shuffled and you're dealt 2 cards. Then what is the probability that both cards are the same suit? So you got like 2 clubs or 2 spades. You know, in Texas Hold'em, you'd say my cards are suited. That's what you would say. What's the probability of that happening? If you Google this problem, there's all sorts of wacky solutions that involve weird brackets and giant numbers that are in the thousands. But if you know what we did in class, you can do this with a probability tree, and all the numbers are less than 100. There's never a number on the page that is larger than 100. And that's why I gave you a little fraction here, but I made it so you can input the top and the bottom. And I want you to try it so you can talk to the people near you. Try to make a probability tree for this, and see if you can figure out what the answer is. I'll give you a couple minutes, and then I'll show you how I do it with the probability tree. And if you do it kind of the easy way, you never need big numbers. All right, go forth and try. Let's take a couple minutes. Yeah, exactly.
What cards look at and then put them back in the deck, right? You wouldn't do that unless you explicitly said you were doing that. I'm going to put this back in the deck. Remember I had it. Trying to certainly supply quickly today. I don't want to
Okay, there's only like 10 seconds left, but almost nobody has answered. Let's put in a guess if you have a guess. I'll give you guys another chance to vote. So if you have no idea, what number should we put in that means that you have no idea? What's a good number that means you have no idea? You put in, don't say it out loud. Okay, you put in 111 and then 111. So if you put in 111 for both, that means I have no idea. Give me some hints, and we'll go from there. Okay. Okay. Let me see how many people know. I did hear some very good questions. People are thinking about with replacement or without replacement. That's because this problem, like almost every problem that you can solve with the probability tree, is secretly kind of an earn problem. This is secretly an earn problem, and the birthday problem is also secretly an earn problem. Okay, let's see what people said. I'm gonna look at the counts. Okay, people said 111. Very good. Most people don't know. Very good. That means we're gonna learn something. Okay, 156, 4. Let me see. Are there any of my favorite numbers on here? 13, all over the place. Okay, I don't think anybody really has it. Okay, on the bottom, same thing. If you typed in 2652, that's the big number way. That's the way the internet tells you to do it. That's technically correct, but like way more complicated than it needs to be. So let's do this as an earn problem. We're going to draw a little probability tree and see how that goes. Okay, so here we go. We're going to try the dot cam. Okay. So why do I say it's an earn problem? Because a deck of cards is like an urn that has 3 or 4 types of balls. There's 13, 13, 13, and 13. Those are the 4 types of balls. We only care about the suits. So there's 4 types of balls in our urn of balls. Right? The balls are actually suits. This is the thing. This is why we do earn problems. Nobody actually cares about urns like an actual like clay thing with balls in it. In every problem, like what is the ball and what is the urn is going to be different, right? The urn is the deck, and the balls are the 13 of each suit. I could draw, if I was fancy, I would draw like hearts, clubs, spades. If you're fancier than me, feel free to write them. But now let's use this and think what happens when we draw 2 cards. When we draw 2 cards, we're going to get a nice tree here. You could draw 4 things coming out of the first bit. You could draw 4. You could have 1 for what happens if we draw a club, what happens if we draw a spade, what happens if we draw a heart. You could do that. It turns out all 4 cases are the same. So I'm just going to draw 1 arrow. This is our first card. And after we draw our first card, what is left? Well, there's 12 of one type, 13 of the other type, and so on. Okay, and this happens with a 100% chance. Okay, so you start out with 13 of each. You drew 1 card. Now there's 12 of one and 13 of the other ones. And the 12 here is the number. The suit here is the first card suit. First card suit. And once again, I'm simplifying things. You could do like 4 cases that are each 25%. And have 4 different cases. You would have 4 different 12, 13, 13, 13s. It's up to you, but this way is a little bit easier to see because, that's all we care about. You guys with me so far? Any questions or comments? I'm seeing some people nodding. That's good. Yeah? So what I'm saying is, it's not that 12 means there's 12 clubs left, or 12 means there's 12 spades left. There's 12 of whatever suit the first card was, and there's 13 of the other suits. That means that these are the other suits. The other suits. Okay. So, yeah, don't think that there's always 12 clubs or something. That's not true. But it is true that there's 12 of whatever the first card was, and there's 13 of the other suits. Okay, and now this is where we do our probability tree. 2 things can happen. Either you get the same one again, okay, and if you get the same one again, you go to an 11, 13, 13, 13. This is the same again. Same again. Or you go different. 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 Okay, now when you go to a different suit, it's going to be 12, 12, 13, 13. Those are the 2 choices. So all of this is exactly an earn problem. The only little twist I did is instead of labeling them hearts, clubs, spades, diamonds, and then splitting it up, I was like, oh, we'll group all those cases together. They're all functionally the same for us. And that way our probability tree only has 1 branch in it. Okay? But this nice tree, it solves our problem. This is actually the secret probability. In probability, there's always a hard way to do the problem and an easy way to do the problem. Pick the easy way, okay? This is the easy way to do the problem. 1 little branch here. If you look at this, if you figure out the probability of these branches, which we practice, then you will know the answer to the question. So let me open the question again. I'm going to reopen it. Now you have this as the hint. Feel free to talk to your neighbors that you said hello to, and we will finish this one up. All right. go here. Okay, it's open. You have 2 minutes now to figure it out. 2 minutes.
You might also want to mention that in fact you can simplify it into
Yeah, that's right. And the reason I did this is because I'm going to go to 3. The next problem, we're going to just add a branch. So if I would have simplified it too far for the next problem.
Right.
But it's true for this problem.
But for this problem, you can simplify another step,
Yeah, that's
which I use as
Okay, there's like 20 seconds left. Again, if you're totally lost, it's fine. Put in 111, and I will know. All right, 8 seconds. 3 seconds. Put in your final guesses. Okay. Let's see what people said. What did people say? Okay. Let's stop the timer so it doesn't ring again. And people said, in the top, most common answer was 12. 12 was the most common answer in the top of the fraction. And in the bottom of the fraction, the most common answer was 51. 51. That is the correct answer. So the most common answer was right. Let me reveal. 12 over 51. Why is it 12 over 51? Let's look over here at our urn, right? This is the probability tree. We either go along this branch and we get the same suit twice, or we go down this branch and we get a different suit. How many ways are there to go? Well, there's 12 cards to be chosen. So 12. How many total cards are there? 51. So there's 12 good cards. And there's 51 total. Okay, on the other hand, going down here is 39 over 51. All right, so what is the point of this? Is you can take something that doesn't look like a probability tree, doesn't look like an urn problem, and use this probability tree approach. That's the point of this. Next class, we are going to do the next problem, which is 3 cards of different suits. If you're very good, you'll be able to do this quite quickly. And I gave you a hint. The answer is 39 over 51. You just have to add the right branch over here. We'll do that next class, and then you'll see that actually this is the birthday problem. This is the birthday problem. Okay. We'll be around for a few minutes for questions if you want to come on down. Otherwise, we'll see you guys on Monday. Don't forget you have homework too.